Hi everyone. In the previous lecture, we discussed various methods of sampling from a population, and we concluded that random sampling in its various forms can reliably estimate the characteristics of an underlying population. In this lecture, we are going to test that understanding. We shall also discuss a very important consequence of random sampling, the so-called central limit theorem. It is a very popular and important result in statistics, and we shall see how powerful it is. But first, we must introduce some concepts. When sampling, we must decide whether we want to sample with or without replacement. So what does that mean? Suppose your population or the sampling frame is this set of colors on your screen. If you sample with replacement, then it is possible that a sampling unit appears many times in the sample. For example, in this sample, the yellow color appears twice. That is, as if after we select a color, we replace it back in the sampling frame, so its chance of being selected remains the same as before. In contrast, when sampling without replacement, a sampling unit cannot appear multiple times. It is as if a sampling unit is selected into the sample. It is withdrawn from the sampling frame before selecting the next sampling unit. Therefore, the subsequent selections are not independent. Instead, they depend upon what has been selected before. Note, however, this withdrawal is only for the duration of completing a sample. This means later, if we pick a new sample, all the sampling units are available again. Some sample R code is available in the description under this video that demonstrates sampling with and without replacement. While sampling without replacement, the observations are not independent within a single sample, but they are independent when sampling with replacement. Again, consider the same sampling frame. Then draw a sample with replacement. Let's call it sample 1. Note, each observation in the sample is independent of what came before it because the sampling frame did not change. Next, draw another sample. Let's call that sample 2. Due to random sampling, typically the samples will be different from each other. But on rare occasions, it may turn out to be the same as sample 1. The principle to remember is that in independent samples, any differences are purely due to chance. Therefore, across a large number of such samples, if we average the values on each position, then the averages will be almost the same. For example, if you assign a number to each color and then average the numbers for each position, then over infinite samples, these averages will be exactly the same. Over infinitely many samples, the average is called the expected value. Hence, the expected value over each position will be the same. So if we represent the color for each position I with a random variable xi, then the expected value of each xi is the same. In fact, we can drop the subscript and say that all the exis are the same as just e of x. Now with that background, let's test if random sampling reliably estimates the population characteristics. Now how can we do that? Well, let's see if we can guess the population's mean by taking the means of random samples. So suppose x1 to xn represent n independent observations chosen with replacement in a random sample. Since these variables draw their values from the same population, we can call them independent and identically distributed variables, or IIDs as we commonly call them. Suppose for the population's expected value or mean equals mu and its variance equals sigma squared. So what is the sample mean now? Let's denote the sample mean with x bar, and it is simply the average of all the observations in the sample. While this is a particular sample mean, we want to know what is the sample mean on average. Well, the average of the sample mean taken over infinitely many samples is called the expected value of the sample mean. We can compute the expected value of the sample mean by putting the expectation operator E around both sides of the equation on the screen. Notice the right side is an expected value of a sum of variables, and this sum is being multiplied with a constant that is 1 divided by n. We can use some properties of the expectation operator to rearrange this equation. Notice 1 over n is now taken out as a common factor, and the expectation operator applies to each variable individually. This is because the expected value of a constant times a variable equals the constant times the expected value. Moreover, the expected value of a sum of variables equals the sum of expected values. You can see both these properties on screen. Now, although we may have we have many expected values, recall I said all the random variables x1 to xn are independent and identically distributed. So if they are identically distributed, they randomly draw different values from the same population. If that's so, then shouldn't we expect that on average their values will be the same? Indeed, that is so, and therefore we drop the subscripts because on average they behave identically. Hence their expected values are the same, that is E of x. We also showed that in the last slide. Thus we have E of x being added n times, so we can simplify that and find that the expected value is the same as the population mean mu. That is a great result because this means that while there may be differences in individual sample means, on average they will be the same as the population mean. This means that random sampling is a good way to estimate the population's characteristics. Now, although the expected value of the sample mean converges to population mean, we also want to know how much the sample mean varies from time to time. So let's compute the variance of the sample mean. But to do that, note that the variance of a sum of independent variables equals sum of the variances. Also note that variance of a constant times a variable equals constant squared times the variance. So as we did with the expectation operator E, apply the variance to the definition of the sample mean x. Next we factor out the constant 1 over n, and hence it is squared because of the second property of variance on your screens. Next, we apply the variance to each of the individual variables x1 to xn. And as before, we note that they are IID, that is, independent and identically distributed variables, and so there should be no difference in their variances. Hence, we get a sum of n variances. Finally, we simplify that so that the variance of the sample mean equals the variance of the population divided by the sample size n. Now, what do you learn about the variance of sample means from this formula? Note, the larger the sample size n, the smaller is the variance. In fact, if n approaches infinity, then variance of x bar approaches 0. Therefore, if we repeatedly collect very large samples, their means will almost be identical and they will be almost equal to the population's true mean. That is why large sample sizes matter when we want to conduct opinion polls. Now let's see an example to show that random sampling can estimate population mean and variance as described. Suppose we have a box containing 3 balls with numbers 1, 4, and 7. Suppose we can only see one ball at a time and we replace it back into the box. So let's compute the expected value of sample mean and its variance. To do that, we shall use a sample size equals 3. So in each sample, we shall pick 3 balls with replacement. So our first sample turns out to be 1, 1, 1. Its mean value is 1. We also know that 1, 1, 1 combination can only occur in just one order. So its frequency is 1. Likewise, we can see 4, 4, 4 or 7, 7, 7. We compute their sample means and know that these sequences cannot be reordered. Hence, their frequencies are also 1. Next, we see 1, 1, 4. The sample mean is 2, but we know that this sequence can appear in 3 different ways. 1, 1, 4, 1, 4, 1, or 4, 1, 1. Hence, its frequency is 3. So we keep going and list all the combinations, their sample means, and their corresponding frequencies. These frequencies are needed when computing mean and variance. Finally, we tabulate all the different values of sample means and their frequencies together in this table. For some reason, we also compute the sample mean squared in the second column. The reason for computing that will be obvious on the next slide. Note the frequencies of sample mean and its square are obviously the same, whereas the sum of all the frequencies equals 27. Since we have listed all the combinations, we can compute the expected value of the sample mean. The formula for computing the expected value is on your screen, and it multiplies each sample mean with its frequency and sums it all together and then divides the sum by the total of the frequencies. You can compute it yourself. It's a simple calculation exercise and you'll find that the answer equals 4. As we can compute the mean of 1, 4 and 7, we know that the mean of 1, 4, 7 must be 4 anyway. Hence, this expected value matches that. That's a check. Next, we compute the variance of the sample mean. Here we use this formula on your screen, and you can see why we noted x bar squared earlier on, as shown in the table on your screens. We can compute the expected value of x bar squared similar to how we computed e of x bar. And the answer is 18. Now we can compute the variance of sample mean and it is 2. We can now verify whether this matches with the formula we earlier derived. So we compute the variance of 3 numbers 1, 4 and 7 in the normal fashion, that is using the formula of variance that is normally used. And we find that the answer equals 6. We know that the variance of the sample mean equals sigma squared divided by n. When we substitute the values of sigma squared and the small n, we get the answer equals 2. Okay. And that matches with the variance of x bar as we had computed earlier. Hence verified and check. Now consider when a sample is drawn without replacement. Again, x1 to xn are observations drawn within a sample, but now without replacement. Consider the population size equals capital N, and the population's mean and variance are mu and sigma squared respectively. Then, without going into the details, let me state that the expected value of the sample mean is still the same as the population mean mu, but its variance is more complicated as shown on screen. We can verify these formulas by again sampling from the box containing 1, 4, and 7, but this time without replacement. Also, let's keep the sample size as just 2 this time around. Hence, we create all samples of size 2. Note all the samples in red can occur twice because they can be reordered. The samples in black can only appear in one order. Therefore, you understand their frequencies. We can compute the sample means very easily. And then using the formulas we used earlier, we can compute the expected value of sample mean, and it equals 4. This is the same as population mean, hence check. Without going into the details, the variance of sample mean turns out to be 1.5. If you substitute the values into the formula for variance of x bar given in the third line on this slide, you can self-verify that the formula predicts the same value as well. Hence, check again. Before wrapping up, notice if the population size, that is capital N, is very large or tends to infinity, then the variance of x bar reduces to just sigma squared divided by n. This is the same as for the formula when samples were drawn with replacement. Are you surprised? You shouldn't be, because when population size is very large, then sampling the same observation twice has a very small chance, regardless of whether you allow that or not. Therefore, when the population size is very large and sample size is small, then sampling with or without replacement is almost the same. So far we have discussed sample mean and its expected value. But what if we plot all the sample means and see the distribution? So assume that again we sample with replacement and draw n independent observations that are represented by n independent and identically distributed random variables x1 to xn. So x1 to xn are IIDs, that is independent and identically distributed variables. Suppose the population from which we are drawing samples has a mean value mu and variance of sigma squared. Then if the sample size is large, and that usually means that n is at least 30, then the central limit theorem tells us that the sample means are distributed as per a normal distribution, such that the mean of this normal distribution is the same as the original population mean, that is mu, but the variance is sigma squared divided by n, where n is the sample size. So for example, if mean of a population equals 75 and its variance equals 64, and the population distribution looks like the graph on your screens, then the sampling distribution, that is the distribution of sample means, looks like this graph on the right. Notice the mean of the sampling distribution on the right is the same as the population mean on the left. But can you guess its variance if the sample size, that is n, equals 10? Pause the videos here and just calculate it. Yes, the variance equals population variance divided by the sample size, where sample size equals 10, and that equals 6.4. Notice the central limit theorem allows us to have some confidence in the values of the sample mean. Because the sampling distribution of the mean follows a normal distribution, we know that 95% of the time the sample mean will fall within 2 standard deviations away from the true population mean. Therefore, we can say that the sample mean is unlikely to fluctuate all over the place. Obviously, if we want to narrow the possible values of the sample mean even more, we can increase the sample size, that is n. This is because we know that variance of the sampling distribution is inversely proportional to the sample size n. Notice the central limit theorem is a very powerful result because it says that the sampling distribution of the sample mean follows a normal distribution, but it does not prescribe that the underlying population from where we draw our samples must also follow a normal distribution. In fact, the original population can follow any distribution. For example, a binomial distribution. So if you remember the lecture on binomial distribution, P equals probability of success. For example, probability of success of a medical procedure. Suppose P equals 0.3. Now there is one limitation, and that is to apply the central limit theorem on a binomial distribution, the condition in bold must hold. That is, the minimum of n times p and n times 1 minus p must be at least 5. Here n is the sample size. For example, if n equals 20 with the replacement, then we can compute the minimum easily. And it turns out to be 6. Hence the central limit theorem applies and the sampling distribution of sample means follows a normal distribution. Let's see. So if we draw samples of size 20 from a binomial distribution, then sampling distribution of the sample means looks like this graph on your screens. You can see that it resembles a normal distribution. Now we know that for a binomial distribution, its mean and variance are given as per the formulas on your screen. Therefore, the mean of sample means will be the same as population mean, that is n times p. This equals 6. You can verify that from the graph as well, which is symmetric about the mean value of 6. Similarly, we can compute the variance of the sample means. This equals population variance divided by the sample size n, and it is 0.46. Now here's a question for you. If we decrease the sample size down to 10, does the central limit theorem apply? Note you can compute the minimum as on your screens. I hope you can verify that this time the minimum value is only 3 and not 5 or more. Therefore, the central limit theorem does not apply. With that, we conclude this lecture and hope to see you next time around. Goodbye.